This section explains the general concept of S-N curve and how do we establish an S-N curve for a particular construction detail. And then it goes into a detailed explanation of the S-N curve with emphasis on the key definitions that frequently used in the fatigue design. Also, we will earn the knowledge of the buzzwords that are widely used in codes, standards, and reference books that talk about fatigue design. What is the S-N curve? S-N curve is a plot of the magnitude of an alternating stress range versus the number of cycles to failure under that stress range. If you have a specific construction detail like the one shown on the screen, bolted connection, you start to subject this connection to a constant amplitude stress range until cracks. You start doing that for a specific stress range and record the number of cycles required to failure, plot that on the S-N curve. Repeat that for different stress range and plot that on the S-N curve. Doing that for multiple stress ranges and recording the number of cycles required to failure for each stress range, you will end up having scatter points like this. Each point represents a specimen that has been tested under a specific stress range that caused failure at a specific number of cycles. From there, using statistics, curve fitting, and a bit of a safety margin, you should be able to establish the S-N curve that is specific for this construction detail. The newborn curve requires a name. The fatigue community agreed upon naming the S-N curve after the maximum stress range that caused failure at 2 million cycles and call that as reference fatigue strength or detail category and tag the S-N curve for this specific construction detail with this stress range. You could repeat the same process to establish the S-N curve for the most common construction details and tag them with their own specific reference fatigue strength. Normally, S-N curve is plotted in a log scale. Here we are going to dive deep into the key definitions of the fatigue through the explanation of the S-N curve and do some sort of anatomy for the S-N curve by identifying different zones within the S-N curve. So let's get started. There are three key points on the S-N curve. First point is the reference fatigue strength detail category, which we spoke about in the last slide. The second point, we call it the knee point, which is the constant amplitude fatigue limit, CAFL. Rather in ASH2, it is called constant amplitude fatigue threshold, CAFT, and is a stress range value below which no fatigue damage will occur under constant amplitude stress. So if you have a constant amplitude stress and the stress range of that cyclic load is less than the CAFL, it is not enough to cause fatigue damage that leads to failure. So there is no fatigue damage for constant amplitude cyclic loading that has a stress range less than CAFL. The third point, and it's called knee point because the slope of the curve before that point is different than the slope of the curve past that point. Normally M1 equals to 3 and M2 equals to 5 in most of the cases. The third point is cutoff limit, which is sort of similar to the CAFL, but for the variable amplitude cyclic loading. So if you have stresses below the cutoff limit, there is no fatigue failure is expected under cyclic and under variable amplitude cyclic loading. Final point on the curve, we call it the endurance. So this is the maximum number of cycles to failure under a specific stress range. To put that on perspective, let's assume that this is your structure, that the fatigue life of your structure fully charged when it is newly built. This is your structure and you started to subject your structure to cyclic loading. Once the crack initiates, you lose some of your power. When the crack starts to propagate, you lose most of your power or you lose most of your remaining fatigue life. And then once you run out of juice, fatigue failures takes a place. We can divide the S-N curve into three distinguished zones. First zone is low cycle fatigue, and this is where the fatigue stresses exceed the yield strength. And this, as we spoke before, happens at very local spots where you have a high stress concentration, like at well toes next to bolt holes and abrupt changes. The number of cycles required to failure is very, very low. That's why it's called low cycle fatigue, and the fatigue life is very short. The second zone is high cycle fatigue, and this is where you have stresses within the yield strength of the material, and the stress flow is laminar stress trajectories are continuous. The number of cycles required to failure are high. That's why it's called high cycle fatigue. Final zone is the infinite life, where the fatigue stresses are quite low and is not enough to cause fatigue damage that leads to fatigue failure. So within that zone, the fatigue life is infinite. Based on that, we have two types of fatigue life. The finite fatigue life, where a failure due to fatigue is expected, and then the infinite fatigue life, where failure due fatigue is not expected due to low fatigue stresses. As we have been able to divide the S-N curve into three distinguished zones based on the stresses, we could do the same and divide the S-N curve into three distinguished zones based on the number of cycles or based on the endurance. These zones are the plastic region. In this region, where we said before that the stresses exceeds the yield, so there is no point talking about stresses. That's why it is strain control. The second zone is the elastic region, where the stresses are within the elastic zone and less than the yield strength, and this zone is stress controlled. The third zone, where the number of cycles that the structure can take is infinite and there is no potential for a fatigue failure. This is called infinite life, and it's likely to be controlled by a durability limit state. The failure is likely to be controlled by durability limit state.